So our next speaker, that causal inference is so hot right now. We've had, at this conference alone, we've had two causal inference, we've had two casual inference talks, and we had a casual inference workshop on Wednesday. And the meetup a few months ago had a causal inference talk also. It's a really big topic these days. People are really excited about it. And you notice we've been doing a lot of fun facts for everybody. These are like fun, goofy things. Our next speaker says that all facts about her are serious. So please welcome Jennifer.
So the original title of my talk was Deep Down, Everyone Wants to Be Causal. And the reason is that basically we act all the time on our presumed causal knowledge of the world. So think about all the decisions you made today just to get here. What subway were you going to take? What did you eat for breakfast? How many slices of pizza did you have for lunch? Implicitly, all of those decisions you're making were based on your presumed causal knowledge. Sometimes you have data to back that up. Lots of times you don't, right? But we all make sense of the world by thinking causally. Now, luckily, sometimes we do have data to help us make the really important decisions about policy or practice. So I want to introduce a tool to you today that I hope will make using that data to make causal inference just a bit easier. The tool is called Think Causal, and we hope that it will make causal inference easy, understandable, and fun. That's the goal. So I'm Jennifer Hill, I'm from NYU, and excited to talk to you today. So the work we've been doing over the past year or so to build this tool has been a team effort. And I really especially want to give a shout out to George Perrett, who is here somewhere, there he is, who basically took my crazy ideas and turned them into something tangible, which has been super exciting. I also want to give special credit to Joe Marlowe and Junhui Young, who both contributed an enormous amount to the project. Okay, so once again, all the questions that we think about, the things we're trying to solve for policy and practice, they're all causal questions. We can't make decisions and expect we know what the impact will be of those decisions if we don't understand the causal mechanisms involved. And if we get them wrong, what's the cost? Sometimes it's money, sometimes it's time, sometimes it's potential. It could be lives, right, if it's a medical decision. So the cost of getting the wrong answer can be quite high, and so we really should be very careful about how we make progress. Unfortunately, at the same time, causal inference is hard. For any of you who have learned a little bit about it, often I feel like after my causal inference course, people need a little support group because they go in thinking, oh, great, I'll learn all the fancy tools, and they learn, oh, actually, this is just hard. There are a lot of assumptions you have to make. Okay, well, what's the basic idea here? The basic idea is that we want to make fair comparisons, right? So if we've got a group of kids who got exposure to a program and a group of kids who didn't, we're hoping that they're basically exactly the same kids. That's what randomized experiments are trying to do, create replicas of the kids across both groups so that if one group gets high test scores and the other group doesn't, and the only thing that's different between them is the treatment, hopefully we can safely attribute that effect to the treatment and not to something else. But most of the time, we have data that look more like this. The groups aren't the same. So if we see higher test scores in one group than the other, we don't know if that's because of the program or because they came into it with very different backgrounds and characteristics and experiences. Okay. So to make progress, we often make this strong assumption, which is called lots of different things, but today I'll call it all confounders measured, which says, have we measured all the characteristics that predict both treatment receipt and the outcome? If we can confidently say that, we can make some progress. So popular in the last, I would say, 2 or 3 decades have been matching and weighting. Matching tries to create a matched comparison group for a treatment group that looks very similar based on what we can observe. Weighting has a very similar kind of intuition, but the weights can be non-integers. But over the past years, modeling, although maybe a little less intuitive, harder to explain to your grandma, actually has a lot of fantastic properties because it allows us to get much more accurate answers to our questions. So here's the basic idea. Suppose there's one confounder, it's a pretest, and we've got a post-test as our outcome. If we can correctly model the relationship between that pretest and post-test, then for each person who's in the treatment group, which in this case are the red dots, we just need to make a prediction of what they would have looked like in the control group, right? That's their counterfactual outcome. So if we can do a really good job modeling, we actually can make real progress. So all the tools that got thrown out for a couple of decades, we're now bringing back. So we've got a comparison between two predictions is just an individual level treatment effect. If we get a bunch of them, we can average that up to an average treatment effect, okay? That's cool, but what if you've got the wrong model? So this dotted line that's been sitting there the whole time is the linear regression fit. It's not a good fit, right? Linear regression is great for a lot of things, but it makes actually some pretty strong assumptions. So with the advances of machine learning, why don't we take advantage of that? So here I'm showing basically the same response surface, but with the step function here, the blue line just represents one regression tree fit to this response surface, which is doing an okay job. But I want to sell to you the idea of a more complicated model called Bayesian additive regression trees, which is the sum of regression trees. And the BART fit to this model is represented by the dashed lines here. And this extends out if we have many more predictors and more complications in our data. Okay, so from that we can get point estimates for individuals or groups, and since it's embedded in a Bayesian framework, we can get intervals, which is really nice. Okay, so show us the money, what's happened, how do we know this actually works? Of course, in causal inference, we never know. There's no equivalent of the Kaggle competition because there's no ground truth. But what we have in the causal inference world are these competitions that have been run since 2016 in conjunction with the Atlantic Causal Inference Conference, where there are hundreds or thousands of simulated data sets, and teams try to, compete to try to get the right answer. So BART, Bayesian additive regression trees, was either the top or one of the top performers in all of those competitions that have been held so far. And it regularly outperforms propensity score matching and weighting and a lot of the standard things that are popular right now. Also, yeah, a bunch of scholarly articles. That stuff too. This is embedded in a R package that's been around for a couple of years called BART Cause, created by my collaborator Vince Dory, who's an amazing programmer. So this already exists on CRAN. It allows the user to implement BART for causal inference. Shouldn't that be enough? Why doesn't everyone use BART Cause? Well, not everyone uses R. That may seem weird to the people in this room, but not everyone uses R. And some people, this is crazy, don't like to use tools they don't understand. So we thought, what can we do to remedy that problem? And that's what inspired Think Causal. Think Causal is a scaffolded, user-friendly way to access sophisticated causal inference tools. And a crucial piece is that it has educational components that allow for just-in-time learning. So just as you're getting confused about what you're doing, the goal is that you can pop out and learn about it just at that moment. How does it work? To do this, we're going to do a silly thing where I'm going to pretend in a video to be a researcher who looks like this. If anyone can figure out how to stop this thing, I would love to know. Okay. I'm pretending to be a data analyst at the Department of Ed in big city. Oops. I have a BA in economics. I have a master's in public policy. My preferred software package is Stata. I have no formal training in causal inference. I have lots of data, tons of data on all the kids in Big City. And I'm asked to make policy decisions or to help inform policy decisions all the time. So here I am with lots of data, don't know much about causal inference, but I'm doing something that assumes that I know the causal answers to questions. That's a little worrisome. So the research question that today is plaguing me is, does early intervention lead to higher test scores for at-risk children? So indulge me in watching this video. Okay, so I am ready to try this new tool, Think Causal. Anything that can make my work life easier, I am really willing to try. So first, I guess I have to decide if I want to learn or analyze. If I click on Learn, oh, I see there are all these different modules to choose from. I like the fact that there are monsters here. That always makes me want to learn more, but I'm not even sure I have time today to learn something new, so I suppose I'll just jump right into analyzing. Got a little welcome message. And the first thing I'm asked to do is to select my causal estimand, which it looks like is some kind of average treatment effect, and right away I'm not entirely sure what I need to do. So I'm going to click on Unsure, which brings me to this learning module on causal estimands. And it appears that this is embedded within an example about the effect of something called the hypershoe on running times for marathon runners. So it's great that I get to learn about this in the context of an example that I can at least vaguely understand, even if I'm not a runner. First, we start with the factual data, which it turns out are the data we actually get to see. And what I'm understanding from this is that while we can see differences in the running times between the people who wear the shoe and those who don't, that difference isn't necessarily something causal. Instead, we have to think about counterfactuals. In other words, we have to think for each person what their running time would have been if they'd been in the alternate universe where either they were wearing the shoe or not wearing the shoe. Okay, and those define individual causal effects, and I can look at the individual causal effects for all the different runners in the sample. And these relate to the average treatment effect, which is the average of all of those individual level causal effects. And this visual is really helping to cement my understanding of that. So then I proceed to learn more about the average treatment effect. I get to see different kinds of visualizations of what that data might look like. And then I'm tested on my knowledge, which hopefully should help to ensure that I remember it in the future. That's pretty cool. I will go back and learn more about that later, but now I've learned enough that I can make an initial choice, and I've also learned that I may need to revisit this later depending on what I see in my data. But for now, this should do. I'm going to let the program know some features of my study so that it can help me interpret the results down the line. And I know that I don't have a randomized experiment, so I'm going to choose observational here. I don't have survey weights or nested data, so I'll save my design and move on. Now I have stata data, but turns out that is not a problem, even though this is an R-based program. We know R is good at uploading all kinds of different kinds of data. That holds true here too. And it's already classified a bunch of my variables as either covariates or treatment. It correctly classified this. I just need to pull out the outcome from the set of variables and move it over here. Post-treatment variables is a concept that's new to me, but this hover over really helps me understand enough to know that I've classified things correctly. Okay, now I'm moving on to a screen that lets me, I guess, modify some features of the data. So for instance, if I want to rename my variables, I gotta say there's nothing more annoying than inheriting a data set where you didn't name the variables and they don't really make sense to you. So it's really lovely to be able to quickly rename things so that they resonate with what you understand about the variable. I don't have any missing data in this particular data set, but it's nice to know that if I did in the future, that would be reflected here. So I'm going to save and move on, and I'm immediately bumped to a screen where I get to explore my data more visually, which is lovely because sometimes I'm too lazy to do this myself, and I do it after the fact, and it's good practice to be exploring my data before I move on to an analysis. This shows a scatter plot of child birth weight versus their age 3 test scores. And if I throw in a linear regression line, I can see a positive trend there. But what's really interesting to me is the difference between the treated observations, which have been color-coded as yellow, and the control, which have been color-coded as purple. Because what I'm seeing here is that most of my treated observations are down here in this lower end of the spectrum, and I guess that's not surprising because as I'm remembering right now, this program was only offered to children who were low birth weight. So I had forgotten that feature of the data set, and that's going to become really important to my analyses. So I'm glad this plot helped to remind me of that. It's also nice to know that I could look at any particular data point I want just by highlighting it, and then the information will pop up down here. Okay, but I want to explore this overlap issue more, so I'm just going to jump to that section, and I'm going to ask to see an overlap plot based on birth weight, and there it is. So this is confirming what I thought I saw before and what I recall from how the program was implemented. All the kids in the treatment group, this is their distribution of birth weights. These are all on the low end of the spectrum. In fact, there's a cutoff at 2,500, whereas this is a more typical range of birth weights for children, which spans the gamut. And what I am taking away from this is that I probably don't want to be making any kind of causal inference about the children in this part of the birth weight distribution, because there's no one who looks like them who got treated. So there's no counterfactual for them in my data. So that says I really want to be focusing on the effect of the treatment on the treated, which is what I learned from that initial learning module. Great, so I'm going to change that here. I'm going to say no to this. I'm not going to look at subgroup analysis. I'm not going to pre-specify, but it's good to know that I could if I needed to do that up front. And then I'm just going to fit my model. Now I know that some of these fancy algorithms take a while to run, so, oh, well, that wasn't too bad. That's good to know. I'm going to switch this to histogram. So what's going to happen here is I'm presented with a posterior distribution of the treatment effect. I can throw in visualizations for the mean, or median, for confidence intervals. That's really helpful. And then I also get a numeric display here of confidence intervals, etc. Another nice feature is it's interpreting the output for me in terms of a sentence that I could throw in a report or a journal article that uses appropriate causal language. But equally important, if I'm in a position where I don't feel comfortable making a causal statement, I don't think that the causal assumptions have been satisfied, I don't have enough confounders to condition on, etc., then I can use this non-causal interpretation, which will still steer clear of some of the pitfalls of interpretations that often fall somewhere in between. So that's great. I can also download this plot, as I can download any of the plots. Terrific. If I want to see results by subgroups, I could look at something like, oh, what's the difference between the treatment effect for kids whose moms were married when they were born versus others? That's not really interesting from a policy point of view. I was just kind of interested individually since I'm a single mom. But anyway, I will move on and come back maybe for that kind of exploration later. But for now, I really need to get this report out. But that brings me to another issue, which is that I really need to have code that I can share with colleagues. I'm going to want to go back to this analysis later. Some of my coworkers may need to reproduce what I'm doing. If I publish a journal article, I may need to share code. But luckily, if I go to this tab, I see that there's a log of what I did, and in fact, I can download a complete script of everything I've done, which makes what I've done fully reproducible. That is a huge relief. Okay, so it seems like I have all the things I needed. I learned something about causal inference. I got the results that I needed to get. I got some different options about how to present the results. I can download any of the plots I made, as well as the code I used. That really helped me out this afternoon and took what could have been a many-hour or many-day job and helped me accomplish it in just a few minutes. So I'm pretty excited about this new software, and I hope you will be too. Okay, so I swear I'm almost done.
Okay.
So what's next? We still need to build out our analytical and educational components, and for that, we need you. So please try out the software. If it's at all interesting to you, here's the link. Give us feedback in the top right corner. There's a place where you can click to give us feedback. Spread the word through whatever mechanism is your favorite mechanism, particularly if you're happy with it. And join the cause. So please contact us if you are a shiny programmer and want to be involved, or you love causal inference, you like building educational things. We'd love to hear from you. Thank you so much.
Thank you very much.